Hello and xin chào. I am Minh Nguyen, or Nguyễn Nhật Minh. I'm a Light Weber Research Fellow at the University of Michigan. This fall, I'm moving to Kapli IPMU in Tokyo. Last year as Cosmology from Home, I promised that field-level Bayesian inference (API) will deliver optimal cosmological constraints from galaxy clustering. This year, I'm returning to Cosmology from Home to hopefully convince you with our latest results that API can in fact deliver optimal constraints and a significant improvement over standard inference using summary statistics. The results that I will be showing you today was born out of this beautiful collaboration with Fabian Schmidt and Beatrice Tucci and the group at MPA, where I started my PhD and my work on API. The current main scientific target of API is galaxy clustering and the new physics that we're going to learn from the data. In particular, we want to shed light on the nature of dark matter and dark energy, as well as new properties of gravity. In this beautiful cartoon by Jesse Muir, you might notice over the entire cosmic time, there has been a competition between the expansion of the background universe being driven by dark energy and the growth of density fluctuations, as well as the clustering of galaxies being driven by gravity and dark matter. Besides galaxy clustering, we do have other probes to measure fluctuations in the universe. In particular, you might have heard about the S8 tension, which is a discrepancy between the sigma 8 or S8 measurements between the cosmic microwave background experiments and the galaxy weak lensing surveys. Assuming that the S8 tension points towards some new physics, how do we know where exactly the new physics is? Did something change between the early and late universe? Or something is different between the large and small scales fluctuations? This is where galaxy clustering is a perfect candidate to pinpoint the origin of the new physics, because galaxy clustering probes exactly the large linear to quasi-linear scales, but also the late universe. Now, moving on to the observation of galaxy clustering, the reason we are recording the 3D position of galaxies in our universe is because we want to trace the underlying dark matter and the cosmic structures. However, galaxies are biased tracers of the underlying structure, and so we need some model and statistics in order to extract out the information that we are after. In particular, the standard techniques and statistics are that of the 2-point and 3-point correlation functions, or the power spectrum and bispectrum. You might have seen these plots showing the power spectrum and bispectrum elsewhere. They are essentially just the amplitude of fluctuations as a function of the distance separate 2 points in space, or as a function of the particular triangle configurations between 3 points. For field-level Bayesian inference (API), we aim to analyze the statistics of galaxy distribution and clustering directly at the field level. One can imagine converting the 3D positions of galaxies to a galaxy density field by putting, for example, the galaxies onto a 3D discretized grid. One can then analyze this 3D galaxy field either in real space or Fourier space. The importance is that we analyze the entire volume voxel by voxel, or Fourier mode by Fourier mode. So we use all the information there is in the distribution of the galaxies. With all the information we can now have access to. The question is, how much information can we gain? Is it worth the hassle? In this talk, I will show you that the improvement factor going from inference using power spectrum plus bispectrum P plus B to field level statistic API can go up to a factor of 5 or more. This effectively increases the effective survey volume by a factor of 25. First, let me take a step back and describe to you the framework that allows us to analyze the 3D galaxy density field. This density field consists sometimes of up to 1 million parameters, because we need one parameter for each voxel or each Fourier mode. So how can we do that? Well, we built a framework based on Lagrangian perturbation theory and effective field theory of large-scale structure that we name LEFTfield, which I will describe in more details in a minute. The upshot is this framework is differentiable, fast, and efficient. This LEFTfield framework then allows us to start from some Gaussian initial conditions, let gravity do the work, and then evolve those forward. From this evolved matter density field, we can then construct the prediction for the galaxy fields that we should observe, which will then be compared to the actual observed galaxy field, mode by mode in Fourier space, or voxel by voxel in real space. Now, if you repeat this process multiple times, you can construct a posterior for the initial conditions and the cosmological parameters and all the model parameters that go into the description of the galaxy fields, in particular the connection between the matter field and the galaxy fields. We can see that there are many ingredients in this machinery. So in the next few slides, let me describe them in more details. In particular, I will focus on the forward model, which links the Gaussian initial conditions with the model prediction for the non-Gaussian galaxy field. And the model prediction is not perfect. Our understanding of the theory is not perfect. So there are definitely some mismatches or some fluctuations that I will call stochasticities. Basically, they are the differences between the model predictions and the actual observations. Those are supposed to be captured by the EFT likelihood, and so that will also be the second important ingredient that I will be describing. The first ingredient of the FBI framework is the forward model. To understand the LEFTfield forward model a bit more, it's important to examine the nature of the universe that we live in. In particular, we happen to live in a universe where the content and the history of structure formation is dominated by cold dark matter. Specifically, galaxy formation happens over the entire cosmic time, which is a very, very long process. But during this entire time, matter that makes up the galaxies are only displaced by a very small amount. What I mean by that is the spatial region that is physically relevant for the formation of a particular galaxy is very limited. So the effective field theory approach essentially limits the description of the galaxy density field to very large scales, and so all the physical processes that happen on small scales can then be effectively marginalized over. In this approach, one can then write down the expansion of galaxy density field in a Taylor expansion where the operators are constructed out of the underlying large-scale matter density field based on the symmetry of gravity, which essentially is the Einstein equivalence principle. The Taylor coefficients then basically captures the response of the galaxy formation and galaxy distribution with respect to the long wavelength perturbations of the matter field. Non-gravitational but relevant physical processes enters the expansion through the higher derivative terms. All of these are highlighted by the blue block that I have on screen. The small-scale physics that we marginalize over also appears in this expansion as stochastic contributions that I highlight in the violet block. The advantage of the EFT approach is that at each order, there is a finite set of terms that appear. The expansion is further built upon the Lagrangian displacement field that describes the displacement of matter, protogalaxy, and galaxy over the entire cosmic time. This displacement field can be built recursively up to any arbitrary order within LEFTfield. Now, the second ingredient of the FBI framework is the EFT likelihood at the field level. Up to leading order, this is essentially a Gaussian likelihood with a diagonal covariance that captures or describes the galaxy stochasticity. The upshot is that the likelihood compares the data and model prediction for individual Fourier modes, mode by mode. I mentioned that LEFTfield is fast and differentiable. This allows us not only to efficiently evaluate this likelihood, but also to use the gradient of this likelihood and the forward model to navigate the very high dimensional parameter space and identify configuration of the initial conditions that match the actual observation. All right, now allow me to put together the forward model and the likelihoods that I described into action so that you can see how we can efficiently explore the very high dimensional parameter space with LEFTfield. On the screen, I'm showing you two rows. The first row for slices through the data cube, and the bottom row the same for 2D slices through the model prediction cube. At the very top, I have the log likelihood, which indicates how well a model prediction fits the data. So I will start the animation now, where we also start the model prediction from a very uniform field that allows us to quickly then identify the correct configurations that match the data. Two things I would like to point out from this animation. First, hopefully you can see that very quickly we can identify the overdense regions, which are the regions where we have very high signal to noise. It takes the sampler a bit more time to identify the correct configurations for the underdense regions where we have low signal to noise. The second thing I want to note is the fact that I artificially slow down the exploration for the purpose of this animation. In practice, only by 1 or 2 samples, we would be able to identify the correct configurations, or as we call it, the typical set. Great. I think we're now ready to see the results from the work that I mentioned at the beginning. In particular, we performed an apple-to-apple comparison between the constraints you would get from API versus those you would get from power spectrumless bispectrum. What is special is that we ensure that the data entering both analyses are the exact data down to the same Fourier modes. We also use the same forward model LEFTfield, so this is really an apple-to-apple comparison. The only difference between two pipelines is the fact that API analyzes individual Fourier modes, while P plus B summarizes the Fourier modes into configurations of power spectrum and bispectrum. One very minor technical detail before moving on to the result. The power spectrumless bispectrum pipeline utilized a simulation-based inference approach, which is very novel and very exciting for cosmological analysis. I will be happy to discuss that further in details during the discussion. All right. So we're now looking at the sigma 8 constraints from the dark matter halos in n-body simulations. So they are also biased traces of the underlying matter field. I should mention that this is looking at or investigating the clustering of halos in rest frame. So real space, there's no redshift space distortion information in these constraints. So the results we are looking at on the left and right panels are for two different halo samples. These halo samples coming from different simulations with different cosmologies. They are output at different redshifts and have different co-moving number densities. So really, this is a test of robustness of our frameworks. Further, there are results showing on top and bottom panels. So the ones on the top panels are for the analysis cutoff scales Kmax of 0.1, and the ones in the bottom are for Kmax of 0.12. So I will just direct your focus on the left-hand side, where you can see the constraints from power spectrumless bispectrum in yellow and constraints from the API approach in blue are shown for two cutoff scales. First of all, they are totally consistent. This highlights the consistencies of our pipelines utilizing the same forward model and the same modes of the data. Furthermore, you can see there's a significant improvement. This improvement factor, which is indicated at the top right corner of each panel, increases significantly, going from a lower analysis cutoff scale to a higher analysis cutoff scale. So from Kmax of 0.1 to 0.12 in this case. This makes sense simply because when you increase this analysis cutoff scale, you have more access to the nonlinear information in the galaxy clustering data. Awesome. I showed you that there's a lot of information to gain if we move beyond the lower order endpoint functions like power spectrum plus bispectrum combination. But what do we have to do in order to really get there? Well, in terms of modeling, I showed you the comparison sampling for cosmological parameters only sigma 8. Of course, we would like to generalize the framework to allow for the full exploration of the full lambda CDM cosmological parameters. Also, in terms of modeling and moving to the observational side, we also would need to have the redshift space distortion implemented. And further, this line will be survey geometry, all of these observational effects that really need to be taken into account. For example, in a real surveys, we also have systematics coming from imaging and target selections. And if we want to push this approach further to smaller scales, then at some point we also have to worry about, for example, fiber assignment in spectroscopic surveys using spectroscopic fibers. Well, there's another axis. I showed you that we can get more information out from quasi-linear scales just by having access to the higher order impulse function. Actually, all information in the entire 3D field. But of course, we only were looking at one single 3D field, which is the galaxy density field. We can also look at other 3D fields. For example, the fields of galaxy velocity or galaxy intrinsic shapes. We have been using galaxy clustering as test particles. So you can think of that analogy as using galaxies as spin 0 particles. Using galaxy velocity and galaxy shape would be using galaxies as spin 1 and spin 2 particles to test gravity and dark energy. Of course, one can think even beyond the reach of galaxy surveys and connect the field level statistics to that of the secondary anisotropies in the cosmic microwave background CMB. All of these are very exciting. I hope that I convinced you that they are worth pursuing. Thank you for your attention. Cảm ơn. I look forward to our discussion at Cosmology from Home. And between now and then, please check out these Cosmology Talks interviews. The one on the left is for this particular work that I described. The one on the right is a very exciting community effort where we unite together and try to show the community that the beyond 2-point statistics and methods are ready for the ongoing and upcoming galaxy survey data. Thank you.